An electrolytic cell is an arrangement in which an external source of voltage brings about a chemical change. Since electrical energy is put in, the reaction is non-spontaneous. When you recharge a battery, you are actually running them as electrolytic cells. Let's look at a simple electrolytic cell. As shown in the diagram here, it consists of two copper electrodes immersed in an aqueous copper sulfate solution. The electrodes are connected to a DC power supply. When the power supply is turned on, reduction occurs at the cathode, which is the electrode connected to the negative lead of the power supply. Oxidation occurs at the anode, which is connected to the positive lead of the power supply. The reduction half reaction at the cathode has copper-2 ions gaining 2 electrons to form metallic copper. At the anode, copper metal undergoes oxidation by losing 2 electrons to form copper-2 ions. Students often find it difficult to remember the difference between galvanic and electrolytic cells. In galvanic cells, the anode is considered to be the negative electrode, and reactions are spontaneous. The cell potential is always positive, and the change in Gibbs free energy is negative. In electrolytic cells, the cathode is considered to be the negative electrode, and the reactions are non-spontaneous. The cell potential is negative, and the change in Gibbs free energy is positive. Remember, in any cell, oxidation occurs at the anode and reduction occurs at the cathode. For example, an impure sample of copper can be used as the anode. As the cell runs, pure copper is deposited on the cathode. Less reactive metals, such as silver and gold, and non-reactive impurities fall to the bottom as anode sludge. Similar processes are used to produce sodium, magnesium, aluminium, and other metals on large scales. Michael Faraday was the first scientist to quantitatively study electrolysis. Faraday's work can be summarized in his 2 laws of electrolysis. Faraday's first law states that the extent of chemical reaction that occurs at any electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. The electrolyte may be molten or in an aqueous solution. In other words, the mass of an element that deposits at an electrode during electrolysis is proportional to Q, the total amount of electricity passed through the cell. Faraday's second law states that the amounts of different substances produced by the same amount of electricity passing through the electrolytic solution are proportional to their equivalent masses. Equivalent mass can be calculated by dividing the atomic mass of a metal by the number of electrons needed to reduce a cation. The amount of charge Q passed through the cell can be determined from the product of current and time. To determine the charge in coulombs, multiply the current in amperes by the number of seconds for which it was applied. The stoichiometry of the half reaction needs to be considered in quantitative electrolysis. The half reaction relates the number of electrons to the metal deposited. For example, in the reduction of silver ions, 1 mole of electrons is needed for each mole of silver ions that reduce. You know that the charge on one electron is equal to 1.6021 multiplied by 10 raised to the power of minus 19 coulomb. Hence, the charge on 1 mole of electron is equal to the product of the charge on an electron and the Avogadro number. This can be written as the product of 1.6021 multiplied by 10 raised to the power of minus 19 and 6.02 multiplied by 10 raised to the power of 23. Therefore, the charge on 1 mole of electrons is equal to 96,487 coulombs per mole. This quantity of electricity is called Faraday, which is symbolized by capital F. Sometimes, this is rounded off to 96,500 coulombs per mole of electrons. Now use all this information you just learned to solve a problem. A 2.50 ampere current is passed through molten magnesium chloride for 15.0 minutes. What is the mass of magnesium deposited at the cathode? Let's work through this problem together. First, we'll find the charge that passed through the cell. You know that charge in coulombs is equal to the current in amperes multiplied by the time in seconds. We need to convert 15.0 minutes into seconds. 15 minutes into 60 seconds per minute is equal to 900 seconds. The current is 2.50 amperes. The charge that passed through the cell is then 900 seconds times 2.50 amperes, which is equal to 2,250 coulombs. From the half reaction, we see that 2 moles of electrons are needed for each mole of magnesium atoms that form. Therefore, we require 2 Faradays, or 2 multiplied by 96,487 coulombs, to deposit 1 mole or 24 grams of magnesium. Therefore, for 2,250 coulombs, the mass of magnesium deposited is equal to 24 grams per mole multiplied by 2,250 coulombs divided by 2 multiplied by 96,487. Thus, 0.2798 grams of magnesium is deposited at the cathode. The conductivity and molar conductivity of an electrolyte change with the concentration of the electrolyte. As concentration decreases, conductivity decreases for both strong and weak electrolytes. This is because there are fewer ions per unit volume to carry current as the solution is diluted. However, molar conductivity increases as concentration decreases. The variation is different for strong electrolytes and weak electrolytes. Before we discuss the concentration dependence of molar conductivity, we must first understand the idea of limiting molar conductivity. This is the conductivity of a solution as its electrolyte concentration approaches zero. Limiting molar conductivity is given the symbol lambda m0. The molar conductivity of strong electrolytes is weakly dependent on concentration. If we plot a graph of molar conductivity against the square root of concentration, we see that the y-intercept is the limiting molar concentration. The slope of the resulting line is the Kohlrausch coefficient, which depends on the specific salt. The Kohlrausch coefficient depends on the cation and anion charges of the ions formed by the electrolyte. You can classify electrolytes by the charges formed. For example, NaCl is considered to be a 1,1 electrolyte, since the sodium ion is +1 and the chloride ion is -1. Using similar reasoning, you can classify calcium chloride as a 2,1 electrolyte. Magnesium sulfate is a 2,2 electrolyte. All electrolytes of a particular type have the same Kohlrausch coefficient. Kohlrausch carried out studies on limiting molar conductivity for a variety of electrolytes. From his work, he deduced the law of independent migration of ions, or Kohlrausch's law. This law states that limiting molar conductivity can be represented as the sum of the individual contribution of the anions and cations of the electrolyte. For a salt of general form AYBZ at infinite dilution, limiting molar conductivity is equal to Y times the limiting molar conductivity of cation A plus Z times the limiting molar conductivity of anion B. Try to work through this problem on your own before checking the answer. Calculate the limiting molar conductivity for sodium sulfate from the data given here. Sodium sulfate contains 2 sodium ions and 1 sulfate ion. From Kohlrausch's law, the limiting molar conductivity is equal to 2 times the limiting molar conductivity of sodium ions plus the limiting molar conductivity of the sulfate ions. Substituting the values from the table, we get the limiting molar conductivity of sodium sulfate as 260.2 Siemens, centimeter square per mole. The molar conductivity of a weak electrolyte depends greatly on the concentration of the solution. This is because weak electrolytes have a low degree of dissociation as concentration increases. Since the relationship isn't linear, we can't determine the limiting molar conductivity by extrapolating back to zero concentration. At infinite dilution, the electrolyte dissociates completely, but the conductivity is so low that it can't be measured directly. Instead, we can use Kohlrausch's law to find the limiting molar concentration. We can approximate the degree of dissociation, alpha, for a weak electrolyte as the ratio of molar conductivity to limiting molar conductivity. If the molar conductivity and the limiting molar conductivity known, then the dissociation constants for weak electrolytes at a given concentration can be found. Here is a typical problem. The conductivity of a weak acid in solution with a concentration of 0.002034 molar is 5.67 into 10 to the power minus 5 Siemens per centimeter. Calculate its dissociation constant if the limiting molar conductivity is 452 Siemens centimeter square per mole. Try to solve this problem on your own before checking the solution. First, find the molar conductivity using the equation you learned earlier. On substituting the values, we get the molar conductivity as 27.88 Siemens centimeter square per mole. Now, you can find the degree of dissociation for this weak acid, since you know that alpha, the degree of dissociation, is the ratio of molar conductivity and limiting molar conductivity. By substituting the values and simplifying, we get the degree of dissociation as 0.06168. With the value of the degree of dissociation in hand, we can use the equation relating Ka and alpha. Substituting the values, we get Ka is equal to 8.25 into 10 to the power minus 6. The products of electrolysis depend on the nature of the electrolyte being electrolyzed and the type of electrodes used. Inert electrodes do not participate in the chemical reaction. Inert electrodes act as a source or a sink for the electrons, providing a surface for the electron transfer. Platinum, gold, or graphite electrodes are commonly used as inert electrodes. On the other hand, active electrodes do participate in the chemical reaction. Active electrodes are used in the electrolytic refining of metals, which we discussed earlier. Thus, we can conclude that the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis reactions depend on the oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Some electrochemical processes are kinetically very slow. At lower voltages, these processes don't seem to occur at all. In order to make these processes occur, extra potential, called overpotential, must be applied. For example, the electrolytic decomposition of molten sodium chloride will produce sodium metal and chlorine gas. In this case, only one cation, that is, the sodium ion, and one anion, that is, the chloride ion, are produced. Sodium ions are reduced to sodium metal at the cathode, while chloride ions are oxidized to chlorine gas at the anode. The electrolytic decomposition of aqueous sodium chloride solution, on the other hand, produces sodium hydroxide, chlorine gas, and hydrogen gas. In this case, besides sodium and chloride ions, hydrogen ions and hydroxide ions, along with water molecules, are present. Let's look at this process in detail. At the cathode, either sodium ions or hydrogen ions may be reduced. As the hydrogen ion has a higher standard electrode potential than sodium, it gets reduced. However, hydrogen ions are produced by the dissociation of water. Hence, the net reaction at the cathode may be written as the sum of these two reactions. Thus, we have the reduction of water as per the equation shown here. At the anode, too, there are two substances that can be oxidized: chloride ions and water molecules. At first glance, it would seem easier for water to get oxidized than chloride ions, since the electrode potential of water is lower than that of chloride ions. However, the oxidation of water is a kinetically slow process. Hence, an extra potential called overpotential is needed for the production of oxygen. This explains why chlorine, but not oxygen, is produced during the electrolysis of aqueous sodium chloride. The net reactions of electrolysis of an aqueous solution of sodium chloride are as shown here. It is more challenging to predict the products of electrolysis reactions in aqueous solutions. Due to overvoltages, you can't rely solely on standard reduction potentials. Reduction will occur at the cathode, but there are two possibilities for the reduction half reaction. First, ask yourself if the cation is a transition metal or a representative metal cation. Transition metal cations will undergo reduction, since they have favorable reduction potentials. Representative metal cations will be too difficult to reduce. Instead, water will be reduced at the cathode, forming hydrogen gas. Predicting the oxidation half reactions is more complicated. It depends on the relative ease with which the different species present in the solution are oxidized. Halide ions will undergo oxidation to form the diatomic elements in preference to water. However, chloride ions undergo oxidation in preference to water due to overvoltage of oxygen. On the other hand, oxoanions are too difficult to oxidize. So, water is oxidized to form oxygen gas. The ability of a cation to be reduced or an anion to be oxidized not only depends on their standard reduction potentials, but also on their concentrations. Hence, to account for the effects of concentration, the standard electrode potentials are replaced by the electrode potentials given by the Nernst equation. In dilute solutions of sulfuric acid, water will be oxidized to release oxygen gas. However, in concentrated solutions of sulfuric acid, the formation of the peroxydisulfate ion is favored. Let's test our knowledge by solving some practice problems. Try to answer this question on your own before proceeding. Predict the products and write a balanced equation if an aqueous solution of silver nitrate is electrolyzed. Assume that the electrodes are inert. Let's start with the reduction process at the cathode. Silver, a transition metal, has a favorable reduction potential. So, silver ions will be reduced to form silver metal. The half reaction is written out. Since the electrode potential value of water is less than that of the nitrate ion, water will undergo oxidation to form oxygen gas as shown in the half reaction. Now, we can sum the two half reactions. We need to make sure that the number of electrons gained is equal to the number of electrons lost, and then add the half reactions to write the overall equation. Here's another problem. Try to answer it on your own first. A dilute solution of sodium sulfate is electrolyzed. Predict the products of the electrolysis, assuming that the electrodes are inert. We use the same basic strategy as the previous problem. At the cathode, it is easier to reduce water than the sodium ion, as it has a higher standard reduction potential value than sodium. So, water will undergo reduction to form hydrogen gas. At the anode, it is easier to oxidize water than the sulfate ion, since the standard reduction potential for water is less than that of sulfate ions. Water will oxidize to produce oxygen gas. We need to make sure that the number of electrons gained is equal to the number of electrons lost. By summing the two half reactions, we can write an overall equation. Note that H plus OH minus make H2O. If you have ever observed rusted iron, tarnished silver, or the green patina that develops on copper or bronze, then you are familiar with corrosion. Corrosion is the term used to describe the process of the surface of metal objects getting covered by oxides or other salts of the metal. In corrosion, the metal is oxidized by losing electrons to oxygen, forming oxides. Corrosion is essentially an electrochemical process. Let's look at the corrosion of iron, which is commonly known as rusting, in detail. Iron corrodes in the presence of water and air. The spot where the corrosion begins can be considered the anode. Here, iron loses 2 electrons to form the iron 2 ion. The oxidation half reaction has an oxidation potential of minus 0.44 volt. The electrons thus released then move to another spot on the metal, which then behaves as the cathode. At this spot, oxygen is reduced in the presence of a hydrogen ion to form water. The hydrogen ions are believed to be available either from carbonic acid that is formed when carbon dioxide dissolves in water, or due to the dissolution of other acidic oxides from the atmosphere. the reduction potential for this process is 1.23 volts. In the overall equation, iron is oxidized to iron 2 ions, while oxygen is reduced to form water. The cell potential is 1.67 volts, consistent with a spontaneous reaction. The ferrous ions formed are then further oxidized by atmospheric oxygen to ferric ions in the form of hydrated iron 3 oxide, commonly known as rust. It is very important to prevent corrosion because it damages electrical towers, bridges, buildings, which can collapse as a result, and ships, which can develop a breach. Corrosion can also force major industrial plants, such as power plants or chemical processing plants, to be shut down. Hence, corrosion not only results in loss of money, but also endangers public safety. How can corrosion be prevented? One way is to cover the surface with paint or some chemicals like bisphenol. This creates a physical barrier that protects the metal. A second alternative is to cover the surface with other metals, such as tin or zinc. Like paint, this prevents oxygen and water from reaching the metal surface. We can also use electrochemistry to prevent corrosion. In cathodic protection, the metal is coated with another metal that is more easily oxidized. In cathodic protection of iron, iron becomes the cathode and the metal coating becomes the sacrificial anode. Cathodic protection can be used to protect steel pipes from corrosion. Magnesium oxidizes more readily than iron, as you know from the table of standard reduction potentials. In this diagram, a magnesium rod is buried and soldered to a steel pipe. Magnesium acts as the anode and the pipe acts as the cathode. The damp soil acts as an electrolyte. The magnesium rod can be dug up and replaced. This is much faster and less expensive than replacing the pipe itself. Try to answer this question on your own before proceeding. Based on the table of standard reduction potentials, which of these metals could provide cathodic protection to iron? Aluminium, copper, nickel, or zinc? Answer: aluminium and zinc could be used to protect iron from corrosion. As shown in the table, their reduction potentials are more negative than that of iron. This means that they are more readily oxidized than iron. Copper and nickel reduce more readily than iron, making them unsuitable for cathodic protection.